Okay, so in this lesson, this is the second lesson, we discuss some of the consequences of having the matter that in fact is made of discrete units, even if we model this, this material, the matter, as a continuum. So you might recall that last time we have defined what is a fluid, not looking at the inner structure of matter, so the microscopic structure, but rather by looking at how the matter behaves when we apply a tangential stress. However, in order to justify that specific behavior, we were forced to look into the microscopic structure of matter, and eventually we have found that the reason why a fluid has that specific behavior is because of the absence of permanent forces among the elementary units of matter that loosely we have defined as units, even if they might be ions, molecules, atoms, and so on. Now, today I would like to go over a similar topic, but from a different perspective. So let's think of an object. Now, I have here by chance these nippers, so they are wire. This is a wire cutter, and I don't know whether you can see clearly, but this is made by different materials. So the tip, the cutter itself, is quite some good stainless steel, while the handle is plastic. The reason is that it is an insulating material, just in case you are cutting some electrical wire. Now, assuming that I asked, what is the density of this object? Well, computing it would be quite difficult, but since our primary school, or at least the first years of the secondary school, we have been taught how to do it. So we take a scale, we put this object on a scale, and we measure some mass. Okay, so let's assume that m is the mass of this object as it comes from the scale. Then we should measure the volume. Now, for simple objects, we have formulas. So if I had to compute the volume of this box, it would be very easy. I would just measure the length of the edges, I multiply them each other, and I get the volume. For an object like this, it would be much more difficult, but a practical way is to take a glass with some graduation on the side. Then we can partially fill it with a liquid, typically water, and then you dig the object into the glass, and then you see how much the water increases the free surface. So the difference is just the volume of the object which has been displaced by the object itself. And then the definition of this ratio, mass over volume, would give the density of this object. Good. But then we should ask a question. What kind of density is it? So you see, this is metal, this is plastic, and so of course this is sort of average density, which doesn't make us so happy, because we know that objects are much more complex. In particular, if I have an object, a typical multi-component, multi-material object, each part could be made of different materials. If you wish, we could use different colors. And then density, once you measure in this way, is only an average quantity. So I using this definition, I could not tell the difference between density here, density here, density here, or density here. So the density I have in mind is more a field function. So the density, which is a function of space, and maybe also in time, in case this object is changing composition, but we will neglect for the time being this further dependence. So it means that if this is my reference frame, and I focus on this point, so this would be the position, and then I would like to know what is the density at this point. So what do I do? Well, it is not very different from what I've described here, because all I need to do is just to restrict the mass and the volume. So what I do is nothing but taking smaller and smaller portions of the object. The smaller the portion of the object becomes, the smaller would be its mass, but the smaller would be its volume as well. And so the ratio, hopefully, would converge to some finite limit. And then what I should do here would be just take the limit for, say, well, let's call it delta V, the volume of this portion. So the limit for delta V approaching 0, delta M by delta V, being delta M nothing but the mass of the finite portion of the volume I'm considering. Well, this is no surprise. We knew that this is the case. However, this is not as innocent as it might look, because if we don't make an additional assumption, this limit would not be defined. And this is where the surprise comes. So let's try now to make a zoom on what is going on here. Well, if I just take this region and I try to draw it larger, now let's pretend that I'm zooming this region. Well, what I get is that I'm focusing on a region like this first, then a region like this first, then a region like this first. Okay? And then I subsequently reduce my interest. Now, X is just this point. Okay? So I really have to shrink this volume to 0. And of course, I cannot sketch this, this concept on the blackboard. I can only approximate it. But then I recall that matter is not continuum at every level. So when I get closer and closer to the point, eventually I find, well, let me use a different color. I don't know if this is visible, but I can try to take some other color. Well, I start finding that matter is made of discrete units. Now, think of these discrete units as gas molecules very far apart, or ions or other atoms hold together firmly in a position. The point is not really their distance or their bonds, but the fact that they are at a finite distance, no matter how small it is, but it is finite, while this is clearly 0. So sooner or later, we will face a problem that this volume is not including anything to measure the mass on. If we want to make this example more extreme, let's focus on a gas, because in a gas it is easier. So we have said many times that an ideal gas, like air, is made of molecules that travel with some random distance. Sorry, with some random velocity. Okay? And of course, since these molecules are moving, how do I define the distance between two of these molecules? Well, of course, there is not a fixed distance, but what I can do is to track one of the molecules in time. Let's pretend this is our test molecule. And then I track its trajectory. Because of this velocity, it will go here, and once here, it will collide with this other molecule. Okay, good. So this is a first collision. I put a cross at this point. Then, because of this collision, this test molecule that would have gone straight will deviate, say, along this direction. But at the same time, there is this molecule moving in this direction, and if they are unlucky enough, they will collide here. So this was the first collision. This is the second collision. Then I can sample a distance, let's call it say L, which is just the casual distance between two successive collisions. Okay? And then I do the same, I play the same game for all the other molecules, and then I get a huge amount of different lengths that I can average together. Well, the average coming from this crazy game is called the mean free path. Okay? Mean free path, which is statistically the average distance traveled by a unit, so a molecule or an atom, in between two consecutive collisions. Well, this is assumed conventionally as the average distance among the molecules. Okay? Now, keep in mind that for air at standard conditions, so temperature of 15 degrees Celsius and the pressure of 1 atmosphere, this length is about 70 nanometers, which might look an incredibly small distance, but in fact it is not, because here the volume is going to 0. So 70 nanometer is big compared to our size, but it is huge. At some point there will be a crossover. This volume will become definitely too big for this distance. So what is the consequence of this finite distance among the molecules? So now let's let's restore the original sketch, and now I draw the volume as it shrinks to 0. So, assuming that the point x that we would like to probe is this one, so this would be the point, then this volume would be this one first, and there is no problem here. I have some molecules. I can count all of them, of course, ideally. I know that each molecule has a mass, and then I sum up the mass of all the molecules, so I know what is delta m, and then I can measure in some way the volume spanned by this set of molecules, and this is delta v, and so this limit, this ratio would be finite, and then I reduce my volume. So this is tending to 0, and then again I have some molecules, I play the same game, and then I have a different limit, and then I keep reducing, but now at some point I will reduce my sampling volume to this one. And then, as you can see, the mass here is not 0. Be aware, it is undefined, because there is nothing to measure the mass on. Now don't be confused, because you might think that since there is nothing, the mass of this volume is 0. Now think of a different example. The age of people. Okay? Now if you have a volume with me inside, then the average would be 54, because I am, at least today, almost 54 years old. But if my sampling volume were this one, then the answer would not be 0, because the answer 0 would be if within this volume there were a newborn baby in this moment. But since there is nothing to define the age on. So the answer is not 0, it is undefined. So as you can see, because of the discrete nature of matter, sometimes we run into an unsolvable problem, which is defining quantities. And this is a general problem. So what happens if you try to define, now take density at point x as a function, say, of the characteristic length of the volume you are using. So one possibility could be that since this is a volume, you take as a characteristic length the cubic root of the volume you are considering. So if you use this characteristics length, you will get a very typical behavior which applies for all kinds of quantities, which is the following. So if the volume is big enough, then you get a value which is independent of the volume itself. And this is easy to understand. Think of the density of air if I use a volume of 1 cubic centimeter, 10 cubic centimeters, 20 cubic centimeters, so I have spheres increasing in radius here. Well, I expect that the density is always the same. But now think of reducing the volume to 0. What happens? Well, maybe, let me see if I can stress this concept. Now, as you can see, initially there are, say, 6 molecules, 6 blue balls, and then there are 3 blue balls, but the volume has not halved. And then if I took something like this, I would have 2 blue balls within a volume which has become very small, so the density would jump up. So what does it mean? It means that the resulting value of density would be dependent on how many molecules I fit into the sampling volume. And since molecules are moving, because we shouldn't forget that each one is animated by a chaotic and unpredictable velocity, these values would fluctuate like a map. It's like sampling the age of people in a cinema. Say, I asked, you enter a cinema, and then I ask, you take the age of 2 nearby people and you make the average. Maybe you go and sample a very elderly couple and you get 85, and then close to them you sample 2 kids and then you get 5. So the average fluctuates quite randomly. However, if I asked you for every projection, what is the average age of all the auditorium, then the average would be much more stable, because if there are, say, animations, you have kids. If there are some for adult movies, then the average would be above. And these quantities do not behave differently. So at some point you will have fluctuations that would become weird, and then you would enter a third region in which the answer is not 0 or something, but is just undefined. Now here I'm using density just to make the example, but the same would apply for many other quantities. Actually, it would be even worse, because the quantity itself might not be defined. So one problem is whether it is measurable, but another problem is whether it can be defined at all. But we will come to this later. And then what happens if I keep increasing capital L, which implies I keep increasing the volume of this, the sampling volume for this quantity? Well, what could happen is that at some point the quantity has a variation, but this time a variation on a smooth base. So what does it mean? If I'm sampling the temperature in this room, as long as I keep sampling air within this room, the temperature is quite stable. But then if the sampling volume gets so big that I get out of the window, then I start sampling fresh air from outside, and then the average would go down. So what happens, actually what do we imply when we ask what is the local value of density? Well, from a mathematical point of view, we are asking the value of density at one point. But the value of density at one point is not defined because of this problem. So what do we mean here? Well, when we ask the value, the pointwise value of density, actually we mean this value. So a value which is stable enough not to depend on the sampling volume. The sampling volume must be small enough not to depend on the field variation of the quantity, but at the same time the sampling volume must be big enough to stay away from this wildly fluctuating value, which implies that the statistical sampling of the molecules is not enough to define the quantity itself. Well, from the point of view of defining the quantity, we are safe, but we have a problem. Because even if the quantity is defined, within this scenario, or within this scenario, we cannot compute limits. And limits are everything in our mathematics. So if I asked, this is an object. This is a single object, like a ball or these dusters or these nippers. So what is the velocity of this object? Well, the idea would be that this object is moving along a trajectory, and then I take the position here, the position after some time, and then I make the difference, and then I make, sorry, the difference in position, which gives a displacement, and then I make the difference, the ratio between displacement by time, and then I take the limit as delta t goes to 0, and this gives the velocity, okay, when this is a displacement, which is a vector. Okay, so you can see that not only in order to define quantities, but also to define other quantities, not only to define variables, but also to define kinematic quantities, we need to do limits. And if we are within this condition, we cannot do limits. What else? What is the surface of an object? Well, you should just compute the integral over the surface of the surface difference. Okay? And this is the area of the surface. But an integral is nothing but the limit of a summation. So this would be the limit as delta si So you might recall from your math exams, Si going to 0 of sum from 0 to n delta Si, right? And again, this can be done because when the extent of the surface approaches 0, again we face the same problem. So if we don't solve this inconsistency, that when the size of the elements goes to 0, we lose the meaning of the quantities itself, if we don't solve this problem, we are dead. All the mathematics we have been learning since our, say, university studies, or maybe your secondary school studies, becomes completely useless. It is an elegant theory, but completely useless for our applications. So, what do we do? Well, we do something which is as simple as it looks, but it has plenty of implications. So what we do is to use a continuum hypothesis. So the continuum hypothesis is the idea of extending our material all the way to 0 dimensions. So what I say is that when I have a material and I have to quantify it, I'm not handling the real material, but I'm handling a surrogate. And this surrogate has the same macroscopic properties as I see from the macroscopic evaluation of the real material, except that it has not a discrete structure, but it has properties and quantities which are defined up to the 0 reference length. This might look a little bit obscure, but I can make an example. So think of the previous volume of air. So in one case, just to make things extremely simple, I will consider a volume of air like this, made only of 2 units, okay? 1 and 2. So think of something which is so rarefied that I have only 2 molecules. And then I ask, what is the density of this material here? Now, in a context like this, we would be here, because when I keep shrinking the volume, eventually I get to some tiny volume around the sampling point, such that there is nothing to measure the mass on. Well, then what I do, I make an equivalence. So this is discrete, and this is continuum. So what I claim is that what I have here is absolutely equivalent to what I have here, except that the matter in this ideal material is not distributed in discrete molecules, but is distributed homogeneously everywhere in my volume. So it is like having say 2 slices of bread. In one you have 2 blobs of marmalade, and these blobs are just concentrated in 2 points, and on the other slice you are allowed to take these 2 blobs of marmalade and spread with a knife all over your slice. Now, of course, this is conceptually conceivable, but we must be sure that quantitatively they are exactly the same thing. So how do we do it? Well, very simple. Let's pretend that these two... Okay, so I was saying, we assume that these two units have mass m and m, and then the total mass of the system would be 2m. Well, my assumption is that now this amount of mass, 2m, is distributed all over the system. Well, just to be more consistent, m half and m half, so that the total mass is m, and then I have another system whose mass is m. And this is easy, but the difference now is that if this were the volume, I will have now this volume. And I can define a density which is defined as this mass by this volume. Now, what is the advantage of having this density? Is that this density is defined at any scale. So, if I take this subvolume, or this subvolume, or this subvolume, up to a point. So when I get here, this is always defined with the same value, which is not true here. Actually, what happens in this case is that if I define, say, this density, let's call rho prime, as the mass divided by the volume, as you can see, if I shrink the volume decreases, but the mass is the same. And then, the more I shrink the volume, the more rho prime increases, up to the point I maintain the two bolts into the sampling volume. By the time I take such a small volume that I have no bolts anymore, I drop into this region where the quantity is undefined. And so I could not make any limit within this context, while I can have a limit, any limit, into this context. So it seems we have solved the problem. However, we should keep in mind that nothing comes for free. And so this approximation has a price, has actually a quite expensive price. So what is this price? Well, I would like this system to be perfectly equivalent to this one, and so it has not to be equivalent only concerning the velocity, sorry, the density, but all the other quantities. Now, just to make things simple, let's pretend that these two molecules, these two units, have opposite velocities. So one has an upward velocity and the other one has a downward velocity. Okay? So I will call V, this vector, let's call it V1 because this is molecule 1, and this would be V2 because it is molecule 2. Then I ask, what is the velocity for this diffused quantity? Well, I might think that since one molecule is going up and the other molecule is going down, the center of mass of the system will not move. And so I assume that the velocity of this continuum material is the velocity of the center of mass of the system at any instant. Well, so far so good. So since here the sum 1, 2 of the vector Vi would be the zero vector, I can assume that the velocity here, that just to distinguish from that of the molecule, I assume that the velocity of this system is 0. And this implies that wherever I sample the velocity, this would be 0. Now, if I asked what is the velocity here, the answer would be the velocity of who? There is nothing moving here. There is nothing to measure the velocity on, while here I can measure velocity anywhere. But now problems come. I want these two systems to be absolutely equivalent. And then I ask, well, here, even if I have two opposite velocities, I have the energy, I have the kinetic energy of the system, and then I can measure the kinetic energy of the system as the sum of the kinetic energy of the two units. Now we should recall that mass was m/2, and then kinetic energy would be 1/2, then this mass, this velocity squared, plus this mass and this velocity squared, but now these two velocities have the same modulus, so it would be 1/2, then again the mass, and then the velocity squared, let's call it v squared, and then I should multiply this by 2 because there are two contributions. So v would be the modulus of v1 and also the modulus of v2. Okay, so here there is another factor of 2, and so I come up with this kinetic energy of the system, which is m/2 times v squared. And now I should move here, but now I'm really in trouble because I've already defined the mass by requiring that the mass of this discrete system is equal to the mass of the complete system, and that's I have. Then I have defined velocity by requiring that the momentum of this system is equal to the momentum of this system, and since the center of mass is not moving here, I have decided to keep it fixed also here, which implies continuum velocity 0. And now I'm dead, because the kinetic energy here is 0 by definition. 1/2 m u squared, but u is 0. Then how do I maintain the equivalence between this continuum system and the discrete system? Well, what I have to do is to invent, is to create new quantities. And then I say, well, actually what I'm defining here is just the continuum velocity. But this is just the mechanical energy. There is another energy which is defined by fluctuations at microscopic levels, so tiny that I cannot appreciate from this point of view, and then I invent temperature. So I invent temperature such that on some scale the temperature gives back the same kinetic energy at the microscopic level. So you might recall that well, depending on the assumptions, there is the Boltzmann constant, so let's call it, say, K Boltzmann, and then there is that V squared, and then if I remember correctly, there is something like 3 halves, and then this constant defines the temperature, and the temperature is again another continuum quantity that I can keep at every discrete level. But this is not enough. There is also another problem that we have to face, and it is the following. Now we need to clean the upper part. If we assume that this is a solid wall, and this is a solid wall as well, okay? Then what happens here? Well, here I have just a medium which is at rest. So whether it is in contact with the wall or it is at some distance, it doesn't make any difference because it is at rest. It's like keeping my hand like this. What happens here? Here I have these molecules who are in motion. And since this molecule, this unit, is pointing at the wall, what happens is that it will collide with the wall and bounce back. Right? So this is the situation at one instant. This is the situation at the successive instant. assuming that the collision is perfectly elastic. Okay? So the velocity will have been reversed. Now we know from the Newton's laws of motion that whenever you invert whenever you change the momentum of a body within some time, there is the impulse theorem. It means that this collision has communicated some force. So the bouncing of this molecule has imparted a force on the wall, and the wall, by reaction, by the third Newton's law, has imparted a force to the molecule which has reverted the velocity. It's like bouncing a tennis ball or a rubber ball, okay? And the collision generates this force. Now, if I think that this is a discrete system, I have that the collision of the molecules against a surface generate a force. And this force I must have also here, but here I have no way to generate a force from something which is at rest, because we shouldn't forget that velocity is zero. And then we are forced to invent another quantity, and this quantity is pressure. So as you can see, as a matter of fact, pressure is nothing but the resultant of the collision forces per unit surface. But why are we forced to introduce pressure in the continuum hypothesis? Just because we cannot keep track of all the collisions of the molecules, just because we have give up with the idea that we have molecules, and we have assumed that our material is smooth and uniformly distributed. And all is needed to get to here in order to be able to compute limits. Now, we will see in the next lessons that the number of invented quantities must increase, and so we have to invent thermal expansion, compressibility, surface tension, water vapor tension, and so on and so forth. Even viscosity is in fact an invention that we have to introduce in order to account for the transfer of momentum among the molecules because of collisions. So once we have clarified that many of the quantities we daily handle to solve our problems are in fact just an invention needed in order to have a continuum model, so you might be surprised to know that if we were able to track the trajectory of the single molecules, probably thermodynamics would be completely useless. Actually, thermodynamics would not exist. The reason why we have to introduce thermodynamics, so temperature, entropy, enthalpy, specific heat, and so on and so forth, is that we are using a material which in fact is not existent. And then the more we want the analogy between the discrete system and the continuum system to be true, the more we need to introduce additional quantities to adapt, additional variables to adapt to the multifaceted physics. Well, now one might ask, well, so far so good, I can invent quantities, I can enrich my model so that it is closer and closer to the reality, but is it worthwhile? In other words, how close is this material to reality? Well, the answer, of course, depends on what is the average distance between the molecules. So if I live in a world where the distance is so tiny that I never get to those distances, well, then I'm safe. It means that this model is almost perfect. On the other hand, if I realize by some practical example that this distance is, as a matter of fact, say 2 kilometers, then I'm dead, because my everyday distances are of the orders of meters, tens of meters, centimeters, and then it means that I'm using a completely wrong assumption. Now, as you might expect from your intuition, Fortunately, the common distance between or among the units is usually quite tiny, but it is important to mention that it is usually tiny. So the correct answer would be that whether or not the continuum model is representative of reality depends on a crucial way on the conditions in which we are analyzing matter. And we can make maybe an example. So we have just mentioned that the mean free path of air, which is a measure of the average distance among the molecules, is about 70 nanometers, which is quite a tiny distance. But why do we have this tiny distance? Well, the reason is that we should count how many molecules we have in a cubic meter, and then we should count how much mass we have in a cubic meter, and then we should start computing. Now, the idea might look weird, but it is quite simple. So maybe I can sketch the basic arguments, and then you can do your calculations yourself. So how do we proceed? Assume that you have a cube whose edge is 1 meter. Then, of course, your volume would be 1 cubic meter. Well, and this is, I would say, offensive for a student of an engineering school. But then we ask how much mass do we have into this volume, and now it depends on the condition. So let's start from standard conditions, so air at at ambient conditions. So the density of air at ambient conditions is about 1.2 kilograms per cubic meter. So it means that within 1 cubic meter I have 1.2 kilograms of mass. Now, how many molecules? Well, this is a bit more involved, because counting molecules, of course, is hopeless. So what I should do is to find a way to connect a number of molecules to some mass unit, and fortunately we have the Avogadro number. Okay, so we know that the Avogadro number, which is about 6×10 to the 23, is the number of molecules. So let's call molecules per mole. So what is a mole? Is a quantity of mass expressed in grams equal to the molecular weight of the substance. Now, air is not a pure substance. It is just a mixture of things, of gases. However, the most common are oxygen, oxygen in molecular form, so it would be O2, and the molecular weight would be 32, and then nitrogen, also in molecular form, in the molecular weight would be 28. You can look from the periodic table of elements. Now, if they were 50-50, the molecular weight of air would be 30, but nitrogen is more abundant, and so I would say 29. Okay? So it means that 29 grams of air contain this number of molecules. So in a cubic meter we have 1.2 kilograms, so it means 1200 grams. And then the number of moles would be 1200 grams divided by 29 grams, which is 1 mole. So it means, maybe I can write it here. So the number of moles would be, for air, 29 sorry, 1200 grams, so let's put it here, divided 29 grams per mole. So if it were 30, this would be 40. Since it is 29, it is something like 41. So about 41 moles. But each mole has this big number of molecules, so the number of molecules in a cubic meter, where do I write it? Let's delete it. Let's erase. So the number of molecules in a cubic meter, let's call it calligraphic N, is 41 times 6 times 10 to the 23. Now this would be 246, and then this would be 2.46 10 to the 25, which is such a huge number that I have problems in pronouncing it. So 10 to the 9 would be 1 billion, 10 to the 18 would be 1 billion of billion, so in the US it would be 1 quadrillion, and then this 10 to the 25 would be 25 million of quadrillion molecules. So it is almost impossible to conceive. Okay? And then if you work out that you have this volume and you have this number of molecules and you cook a little bit the numbers, well, then you end up with this mean-free path. Okay? And this you can do. However, there is one crucial assumption, that the density of air is 1.2 kilogram per cubic meter. And this is true only at the ground level. Assuming that we are ascending with some airplane or rocket, well, as we rise, the density decreases. And when we decrease this number, this 1200, as we can see, we decrease the number of moles per unit volume, because the volume remains 1 meter. And when we maintain the volume fixed, but we decrease the number of moles, we decrease the number of molecules, and therefore the distance increases, because within the same volume we fit a smaller and smaller number of molecules. Well, now we don't have enough knowledge to make all the detailed calculation, but if you went up to about 140 kilometers of height, so this would be the elevation, so it is aerospace height, well, this mean-free path would be of the order of 1 meter. So this implies that when your distances get below 1 meter, well, it doesn't make any sense distinguishing the continuum model, using the continuum model. And this should be kept in mind, because the continuum model can be used only when the distances in which you are interested in is much bigger than the mean-free path, or anyway is much bigger than the distance among the molecules. So one quantity that is usually defined in order to quantify this concept is the Knutson number. Okay? So the Knutson number is the ratio between the mean-free path and the length you are interested in. So think of, just to fix the ideas, a rocket. So a rocket has a length that can be say, tens of meters. It could be 20 meters or as big as more than 100 meters for the Saturn V or the Apollo missions. But anyway, this is an object whose size is L. When the rocket is lifting off at the ground level, the distance between the molecules, lambda, is just 70 nanometers. So this would be 7 10 to the minus 8 meters divided by order of 10, 100 meters. Okay, this Knutson number is approaching 0. So when the Knutson number approaches 0, then the continuum model is perfect. But then the rocket starts rising up. 10 kilometers, 50 kilometers, eventually it gets to 140 kilometers, the distance I had sketched somewhere. Well, then this becomes 1 meter. And the length remains the same. Actually, rockets have a strategy which is called staging, so they tend to get rid of the exhausted parts, but we will not consider this part. So when this number exceeds 1 or becomes comparable to 1, then the continuum model is not useful anymore, actually cannot be used. Now keep in mind that in this simple example we have considered an object whose size remains constant and lambda changes just because we are changing the ambient conditions. However, you could also have the Knutson number which gets bigger and bigger because lambda is constant but L is decreasing. Think of common everyday devices, okay? So if they operate in air, lambda remains 70 nanometers for air at ambient conditions, but L gets shrinking. So in the 50s, we were used, actually, people living in the 50s were used to handle, say, objects of this size. But then, in the 90s, a new term was generated, which was micro devices. So micro devices means that the devices tend to be of the order of microns, so 1/1,000,000th of meter. Nowadays, we hear more and more frequently nano devices. So a nano device is an object whose size is an order of a nanometer, 10 to the minus 9, 1/1000,000th of a meter. So if this is 70 nanometers, and you have an object which is say 10 nanometers, then this ratio is 7. So you are well beyond this threshold limit, which means that your device is not operating anymore within the continuum hypothesis. So whether or not you can use the continuum hypothesis depends on this non-dimensional parameter, the Knutson number. By the way, it's written in this way. And whenever this number approaches 0, you can use the continuum mechanics, all the analysis, intervals, derivatives. Whenever this number goes to this direction, the only possibility you have is to use the statistics of the discrete units, the discrete molecules. So essentially the Boltzmann statistics. Okay, so what I would like to do, starting from these very basic concepts, is to develop, to build, and to show that thanks to the continuum hypothesis, we can define the fluid properties, and starting from these fluid properties, we will derive the equations and then the dynamics on the fluids. Just a final piece of information. If you try to type on the web continuum hypothesis, it is very much likely that the first items will not be, the first hits will not be this subject, but another one, which is within mathematics. What I've been saying has nothing to do with the mathematical continuum hypothesis, which is a subtle question of the integer numbers versus real numbers. So you should go to the counter sets. Well, it is a quite involved mathematical argument. Good. See you next lesson. Bye.